Screen, you should see a PowerPoint presentation.
Yes.
Okay, good. I think everybody joined by the web client, so it doesn't actually show me what you're seeing. But let's go ahead and get started. My name is Bob Dibner. I work for Corelis. We're a division of EWA. I'm a technical marketing engineer here. I'm also joined by Ryan Jones, also a technical marketing engineer. Ryan will be assisting me with fielding questions at the end. So our agenda today, we'll go over our company background of Corelis and EWA. We'll talk about what Jtag is, authentication and security applications of Jtag, our Jtag interrogation system. I'll demonstrate the system for you, and at the end we'll have time for a question and answer. If a question comes up during the presentation, I invite you to use the chat box to type it in, and we'll get to it at the end. Otherwise, we can also unmute your microphones at the end. So let's go ahead and get started. So who is Corelis? We were founded in 1991, so we celebrated our 25th anniversary last year. We're based in Cerritos, California. It's in Los Angeles County. Our main focus in products is test access for electronic systems. So we specialize in the Jtag standard as well as I2C and additional serial bus interface standards. Our line of Jtag tools, which we'll see later in the presentation, is pretty much our main product. And we do provide products and services that are commercial, unlike our parent company, EWA. So we were acquired by EWA in 2006 and have been an EWA company for 11 years now. So EWA was founded in 1977. EWA stands for Electronic Warfare Associates. We often support EWA in projects that can utilize our products. So they're headquartered in Virginia. We're in California. They apply their services to a broad range of technology, whereas we're more of specialists here. And EWA focuses on government contracting, whereas we are commercial products. So I'd like to talk a little bit about what Jtag is and what our tools can do with it. So the 1149.1 standard, commonly referred to as Jtag, it's been around since 1990. It's been continuously updated over time. There have been extensions to the standard, additional standards that are adjacent to this standard, as well as updates to the standard, the most recent one being in 2013. Jtag stands for Joint Test Action Group, which is the association that originally developed the standard. That's just a little bit of history for you there. There are many existing standards from IEEE that use the Jtag port as the access mechanism. There are also some new standards in development also using the Jtag port as access mechanism for them. For example, there's one being developed for testing 3D ICs. So Jtag is a hardware access port for electronic systems. The main application is system test and debug. So you'll see a lot of products that use Jtag for testing assembled circuit boards. They're also very common to use Jtag to access CPUs for debug features. And one of the things we're going to take advantage of is Jtag includes electronic identification features, and we'll go over those later in the presentation. I do want to mention that Jtag, if you're not familiar with it, it's very common in components like microprocessors, FPGAs, ASICs often implement a Jtag port, and definitely anything programmable often will have it, CPLDs, both CPLDs and FPGAs. So traditionally, Jtag applications were for boundary scan test. So they've extended way beyond this over time. Nowadays, Jtag is used in system programming, in circuit debugging, all sorts of applications using Jtag. I'd say more recently, Jtag has been used in digital forensics. So we hear from a lot of people that they're using it to read data off of mobile phones to obtain data from flash devices that are connected to a Jtag component. So because Jtag can provide access to the CPU on a system, it can be used to read flash memory from devices without even having to remove that flash component. So it's very useful for things like that. It should also be noted that many components support both the basic boundary scan features of Jtag and they also implement their own features using the Jtag port. So some of these may be things like built-in configuration of an FPGA, reading back the configuration data from that FPGA. It could be controlling a CPU. There are many test features that people are implementing and using the Jtag port as their access mechanism. So here's a diagram of the basic system architecture of Jtag. So a Jtag controller, which in our case is a laptop with a Corelis USB to Jtag adapter, connects to the test access port of the or the tap of the electronic system. So the tap is a physical port that we connect, for example, a ribbon cable to. Jtag compliant devices can be daisy chained within the system. So in this case, we see 3 devices daisy chained. And they can be brought out to a single tap connection, which we show in this case, or there can be multiple tap connections. For example, we sell controllers that have 8 taps for large systems that may have multiple Jtag connections to them. And additionally, multiple boards can often be connected together, and the Jtag chain can move through the Jtag compliant components of multiple boards. For example, you may have boards in a backplane system where the Jtag chain provides access to individual boards as well as maybe components on the backplane itself. So Jtag is a physical access mechanism, but the physical access mechanism is not well defined in all cases. So the standard defines the 5 signals. It does not define the electrical parameters of those signals. So for example, the voltage, interface voltage is not going to be standard. It may be 3.3 volts, it may be 2.5 volts, it may be 1.8 volts. It's not defined by the standard. The standard also does not define the pinout. So every vendor has their own pinout. We have our own here at Corelis. Altera has their own, Xilinx has their own, Intel has their own, and so on and so on. So one thing I want to mention is even if a board doesn't have a connector, it can often be possible to attach wires to the PCB, or as we see in this photograph here, there are some cabling systems that can do just by physical contact without soldering down or having a header on the board, you can make contact to do Jtag scan tests. I do also want to mention that our controller, the one that's included in this system, has variable voltage, so we can accommodate, for example, a 3.3 volt part or a 1.8 volt part. So next I'll talk a little bit about Jtag authentication and security. Excuse me. One of the great things about the 1149.1 Jtag standard is that it includes a standard for documentation of those components. It's called the Boundary Scan Description Language, or BSDL. BSDLs are generally provided by the vendor. You can often find them on their website, or if you can't find them on the website, you contact the vendor and they can send them to you. So the BSDL files include machine-readable information about the component. It includes an ID code, which is in turn composed of a manufacturer code, a part number, and a revision code. It also defines information like which opcodes are available for that device and basic information about what those opcodes do. The end result of this is we can use a BSDL file. Our software can read in a BSDL file and determine the expected parameters that we would read back from that device, and then we can use our Jtag controller, read back the actual parameters, and compare actual to expected for a pass or fail test. And since these are electrically accessible, we're just using a 5-pin, 5-signal Jtag port. We can do all this in non-destructive manner. We don't have to take any chips off the board to read information about them. We can do it in system as long as the Jtag port is available to us. So it also means that even if a counterfeit component were, for example, remarked, if they blacktopped it, put new revision markings on top, we would, if it's an old revision part, be able to tell that from the ID code because the revision code would not match and it would be a suspect component at that point. So in addition to the identification features built into the original Jtag standard, the 2013 update to the Jtag standard added a new electronic chip identifier, or ECID, definition. So the ECID is unique to an individual component. We can read it. It acts kind of as a serial number for each individual chip, as long as it supports that feature. This is an optional feature. The vendors are not required to implement it, but some of them have. We can use that serial number, which is hard-coded into the component at the factory, to trace, for example, a component through the supply chain. So vendors could use the ECID to validate whether a component is authentic or not by keeping good records of that component through the supply chain. So the end user gets the component, they go back to the factory, they ensure that that was actually a factory manufactured component. So as mentioned earlier in the presentation, the BSDL file defines available instructions and the information about what those instructions do. So in most cases, those instructions are going to provide access to registers on the chip. Additionally, the Jtag standard says that if an instruction is not documented in the BSDL file, then it should connect us to a very specific register. It's a single bit bypass register. So based on that information, what we can do is we can use this information to send all possible instructions to a component or a series of components. We shift data through each component. We characterize the register length and data contents, and we use that for comparison against the component documentation. So, excuse me, the undocumented instructions could then be further investigated. You can do a more thorough analysis with your list of possible instructions that were not documented by the vendor. So Jtag uses shift registers to manage data transmission. There's two types of registers. There's an instruction register and a data register. So the instruction register is mandatory and can be any length. The length is defined in the BSDL documentation. If a component conforms to the Jtag standard, it will always have an instruction register for loading instructions. So once we have that information, we know how to load instructions into this component. We have everything we need. So once an instruction has been loaded, we see in this animation here, it connects us to a data path. So the instruction opcode defines what the chip is going to do in response to that. It's going to connect us to any number of data registers. It could be a custom register. It could be a register defined by the 1149.1 standard. So for example, if we shift in the ID code instruction, it connects our data path to the 32-bit ID code register that's defined in the Jtag 1149.1 standard. The standard also allows for custom registers. Vendors can implement any number of custom registers, but the standard mandates that these registers be documented in the BSDL file. So we have a case study of some research that was done in 2012. Researchers, I'm not going to pronounce his name correctly, Skoro, Bogatov, and Woods used techniques similar to what we do here to find all undocumented instructions for a component. So they use this technique to limit the scope of their search. They determined which Jtag instructions actually return data and seem to access some amount of functionality. From there, they were able to, using more time-consuming techniques, probe the component behavior and determine that certain instructions gave them access to key information from the chip. This was widely published in 2012, and you can probably find articles about it as well. Now I'd like to talk about our Jtag Interrogator system. So you'll see an image here of our C100 USB to Jtag adapter connected to what we have here is a SmartFusion 2 development kit. So the system consists of a hardware component and a software component. So on the left we see our USB to Jtag hardware interface. On the right we see a representation of our software component. It's a Windows-based software. It runs on any Windows PC. We provide a one-to-one interface cable with the controller, but unfortunately because the standard doesn't define pinout, that interface cable is only going to work if somebody designed the board around the Corelis pinout. We have adapter cables, or you can fabricate an adapter cable to connect to other targets. Depending on if it's a popular target, Altera, Xilinx, we probably have adapter cables already. If it's a less popular pinout, we may not have one, but you can always fabricate a cable to connect to that board. So talking about the system highlights, The Jtag Interrogator system has three main functions. So after a project is created, it can be used to identify and compare Jtag-related data from a target system with the expected data from the BSDL documentation. We return a pass or fail result, whether the pass indicating the data matched, a fail result indicating there was a mismatch between the actual data read back from the physical device and the data expected based on the documentation provided to the tool. We can also read and report an ESID value if present. The ESID read is integrated into the identification feature, so when you look at a component that has an ESID capability, you'll see the ESID value listed. The tool also includes what we call an opcode discovery module that runs the process we described earlier of scanning out every possible opcode and looking at the data register that it connects to and then comparing that against the documentation. So this will try all possible instructions. If it finds an opcode that returns data that's not the bypass register, it will report it as an undocumented instruction. It will return the expected and actual register length, and it will return the contents of that register. So using Jtag has its advantages and disadvantages. So our main advantage is speed. The scan process takes just a few seconds. You'll see when I do the demonstration that it's very quick. Additionally, because we use an electrical interface, the physical properties of components, such as the markings, the package, they do not affect our tests. Somebody could repackage a die and we would be actually looking at the die itself, not the package on the outside, and it would not affect whether we can identify that as what we expect it to be. The equipment is very low cost compared to electrical parametric test equipment like curve tracers that are commonly used for identifying counterfeit suspect components. It can also be used to access components that are either on a PCB, or if you have a component that has not yet been populated in a system, you can usually make a test jig of some sort and use an IC socket, something to access the chip with our 5-signal interface. There are, of course, requirements that need to be met to be able to use Jtag in the first place. Of course, components must have the Jtag capabilities built in the, at the factory. Essentially, when they're designed, it has to have Jtag built into it, and that has to be brought out to some sort of connection. It can be an actual physical connector that we connect to. It can be pads on the board that a bed of nails fixture can connect to. We just need to be able to make electrical connection with that Jtag port. Unfortunately, these are complex digital circuit or semiconductor components, and they don't all follow the same package style, so it can often be difficult to find a socket for a particular component to gain access outside of the system. So there may be some, for example, non-recurring engineering costs to develop a test jig to gain access to that component outside of a system. And finally, there are security features that many manufacturers use for Jtag. The Jtag port can often be locked down by fuses after manufacturing. So even though a system in the field may have a Jtag port, we may not be able to access it because it's been locked previously prior to going to the field. And now I'd like to demonstrate the tool. So let's bring up this. Let's see if I can resize this to make it a little better. So this is our Jtag Interrogator software. I have a project loaded for one of our prototype boards. This board has 5 Jtag components. Here's a photograph of it. So we have excuse me, a Microsemi Igloo 2 component, a Xilinx Spartan 6. We have an Altera Max 10. U3, I actually don't recall what that is. I'll have to look. And we have a TI CPU, an AM335 series CPU. So I've previously created a project for this. I called it the ScanExpress Demo Board. It's our prototype for a demonstration platform that we use for our boundary scan tools. So from here I have options. I can scan one board. I can scan a board lot. So this would be used for vendors that are accepting a lot of boards. They want their operator to bring in many boards at one time and create a report for all of them at once. We also have the opcode discovery module that was mentioned earlier. So let's go through the scan a single board process. So I click the Scan Now button, and in a very short amount of time the test passed. It reports that I have 5 devices on my chain. I have 5 complete matches, everything matched, no mismatches, and I have a report that I can view for details. So I click View Report. Let's make this bigger. Actually, I can zoom in this way too. I hope that's fitting on everybody's screen. So I'll see that I have 5 devices in the chain. I have a table listing the devices. Let's see, what was U3? It was an Altera 5M, so I believe that's a Max 5. And we can see the detailed results. So in each case, we list the ID code and the boundary scan register length of a component. If these were to mismatch, we would report it, and that would be a good indication that the component that's on the board is not what we expected to be there. So we can look at some details. We do an implied ID code test, which means that we reset the chain, then we read the ID code out that way. We also use the ID code opcode to read the ID code. We read a user code, which in most cases is going to be don't care because that's defined by the user. If you had a component that you wanted to test that, you could just by adding a user code to the BSDL file. We test the boundary scan register length, so the boundary scan register being one of the registers that is required by the standard and defined in the BSDL, so we know what the length should be and we can test what the length is. And skipping back to the beginning, our first test is the IR capture test. So in this test we read back the instruction register. We have an expected pattern. It's always going to end in 0, 1. Sometimes the vendor will define a pattern that we can use. In this case, the expected pattern was don't care, so a pass there does not really give us that much information about this component. Wanted to show you. So in this case, we mimicked an ECID. Unfortunately, this component does not have an ECID, but we were able to use the ID code register to mimic an ECID register. So when the tool does know that there's an ECID available on the component, it reports back the value. In this case, 020A 50DD. Which you may notice matches the binary value for the ID code because that's the same register that we used. It also reports the length. If the length mismatches, it will cause a failure in the test. So that's the board scan process. This can be used for identifying mismatches between the actual component on the board and the component documentation as defined by the BSDL file. So let's go ahead and close that now. I'm done, and all of these reports get saved in the tool for viewing later. So now I'm going to run the discover opcodes function. We provide a warning and require the user to acknowledge that they understand the risks. When we shift out all possible opcodes, we do not know what those opcodes are going to do. They could cause harm to the board, they could cause it to lose its configuration information. We simply do not know what they're going to do. Luckily, I've tested this board before. I know that nothing harmful is going to happen, so I'm going to go ahead and run it. So the scan takes just a few seconds. It finished, and it gives us a summary report. So among all my components, I found 236 opcodes. I found 115 of them that were not listed in the BSDL file documentation, and I can view a report to get some details about that. So hopefully this is readable. Let's make it bigger. So here we see our first component, U1. We have a few opcodes up here that have either mismatched or were not found in the BSDL. In this case, we find that we shifted the opcode for the in-test instruction. The BSDL said we should have received a register of 666, but in reality we got 1. So we report that as a data register length mismatch. In this case, we shifted out instruction 1001. It's not defined in the BSDL file. We received a boundary scan register length of 666, and we report the pattern as well. Now in this case, it looks like that instruction more than likely connected us to the boundary scan register, as we see that the results here match very well with the XTest instruction. So this may be not a harmful instruction, but we really don't know what it does, so we could go back to the vendor and ask them to give us more information on that to complete our documentation of this system. Now on the same component U1, we have many registers that were returned with non-bypass data that were not defined in the BSDL. We see some 32-bit registers, we see some 8-bit registers, 16-bit registers, some more 32, 64, greater than 5,000. At this time the tool stops at 5,000, so all that means is it's somewhere in the greater than 5,000. It could actually be not a complete register. It could connect us to something else that just doesn't behave as a shift register. We don't know. We have to stop at one point, and right now that limit is 5,000 bits. We see some 128, 129-bit registers. And all of this is data that you could, for example, take back to the vendor and ask them to provide clarification on what these things are doing. It could also be used for correlation analysis if you want to compare this component against another one and figure out why this one has registers that another one does not. Now we'll see, excuse me, that U2, on the other hand, has no undocumented instructions. Everything that we found, well, I should say, yeah, it has no undocumented instructions. The IC program register that we see here is a very long register. It's more than 5,000 bits, so we don't scan the whole thing. More than likely, if we did, we would get a DR register length match. But in this case, the vendor provided complete documentation in their BSDL. They did note that some instructions are private, and we, by default, skip private instructions. You could override that by altering the BSDL file, but as the tool works right now, we do not shift private instructions. These are acknowledged by the vendor as being for internal use only. So they could cause harm, they could be used for other reasons. We do not test those. So there's quite a contrast between this component and the previous one. This component is very well documented. All opcodes are documented, at least acknowledged in the BSDL file. So this vendor has actually provided more information about their component. Again, U3, we find a few registers that were not documented. 13-bit register, 16-bit registers, 142-bit register. We notice that none of those correlate with any of our other registers. It doesn't look like it connects us to the boundary scan register, so that may be something that you go back to the vendor and find out why this register exists. And that's about it. This is just more of the same. We'll see U5 is also well documented. U5 is a CPU. The vendor provided complete documentation for that. They either labeled the instructions as private, or they gave us documentation on how to use those instructions. So these reports can be exported as CSV files if you want to record a lot of data. That can be useful. They can be printed to your local printer to a PDF file if you like. And that's about it for the tool. So I'd like to open it up to questions now. And I think everybody is unmuted, or at least you have the capability of unmuting yourself.
Hi Bob, this is Joel. So I have a couple of questions actually. So first part of your presentation, you mentioned that you're gonna detect counterfeit ICs. Could you explain a little bit more about how you're gonna do that?
So of course it's going to depend on the class of counterfeit component. If, for example, you have an old revision part remarked as a new revision part, which is one class that we've heard people reported, in that case, we should read from the die itself the old revision ID code. That would be a mismatch. We actually had saw an actual case of this once, or at least on one occasion that I'm aware of. So that would tell us that it was an old die remarked as new. I guess another case would be a component remarked as the different component. So if you have the same two completely different components in the same package, and one of them gets remarked to pretend that it's another component, that's another case, because we would attempt to read the JTAG information from the component. It would not match what we expected, and we would be able to flag that as a suspect.
Yeah, the reason I asked, because those IDs, what you were saying, EC'd, I believe those are programmable, right? Or they are fixed for a particular
the ID code is fixed. The ECID, it's really up to the vendor on how they implement it. So one of the main implementations would be something like anti-fuses, so that at the factory, the serial number is burnt into it.
Right.
But it's not likely to be user programmable. The only ID code that's user programmable is the user code opcode, and that one in general we just treat it as don't care, because it's not going to give us much information at all.
Right, right. Yeah, yeah, thank you. And I have another questions regarding, so I think you are familiar with Jtag, right?
Yes.
So IEEE 1687.
Mm-hmm.
So there you basically restrict the use of your internal instructions. So do your tool kind of like have those features to access the internal instructions, or it is in the...
Well, even with iJtag, it's still the JTAG interface is scan-IR and scan-DR, which is what we're kind of doing here. We wouldn't be able to access the internal network. 1687 defines a pretty complex ICL definition, so the instrument connectivity language that defines a network of instruments within the chip. We can't dig down into that network. We would only be doing the raw scan-IR, scan-DR. So if something is more complex than just scan an instruction, it connects you to a data register, we couldn't drill down into that with this tool.
Okay, okay.
I'm not sure that would even be possible. We rely on being able to scan these in a reasonable amount of time. When the instruction register lengths get very long, the amount of time that this test would take is very, very long.
I see. Yeah, thank you.
Out of curiosity, do you have experience with 1687 components?
I actually have some background on that, but not in the hands-on experience. So do we speak like means I am working on that security part, like how can you protect your internal instructions from being accessed. Like if you said that you have a chip memory on the system, and then you have the JTAG access, and then basically you can read out the whole information on the memory, right? So if you are concerned about your system being cloned, then you have to protect some way that that readout access is not done from the JTAG access. Means if you are authentic user, then you can do the readout, but if you are not an authentic user, then how can you basically prevent from readout that the content? And it can be the FPGA configuration files, or like instructions, or memory readout, any sorts. So the objective is like how can you provide some authentications on like who is performing the test.
Okay. Yeah, that's way above and beyond the scope of this tool, but it's always interesting for me to hear about. And of course, JTAG, secure JTAG, like the kind that you'll find in Freescale NXP components nowadays, can be locked down and require authentication. In that case, our tool would not be able to, for example, access that JTAG port to do any sort of tests.
Correct. If you don't provide the correct key, so all the instructions will be bypassed. So you cannot access basically all those secure instructions.
Yes. Do you have any other comments or questions?
I want to hear from some other people and then probably
Well, the floor is open. If you have a mic, please feel free to ask any questions. If you don't have a mic, you can use the chat box, and we'll try to respond.
all right, let me ask you one.
Okay. Sorry. No,
go ahead.
when you were comparing all of the boards against manufacturer specifications, is there a way in your software that we could keep a private repository of manufacturer specifications? Or is this something where it's only your repository of manufacturer specifications?
Well, the manufacturer specifications come from the BSDL files, so we actually don't provide a repository of that, partly because we can't redistribute it.
Mm-hmm.
So
Okay.
let me show you the actual project.
Yeah.
So if we go to, I don't want to open, actually I think I'm not logged in with enough permissions.
No problem.
And I don't remember my administrator account either.
I hate when that happens.
I was writing documentation for this.
Way too much with me.
I was creating documentation for this tool, and I had to write documentation for a user account, and I usually administrator. So I do not know how to log in with that. But what I can mention is the BSDL files are provided by the vendor. We have some amount of information from that. We use the ID code to identify components to help you identify which BSDL file to use when developing the project.
Mm-hmm.
But otherwise, if you have a Xilinx component, you go to the Xilinx website, you download the BSDL file from them.
Right.
If you have a Broadcom component, Broadcom does not make their BSDLs publicly available. You have to go to Broadcom and request it.
Right. Sometimes we do work looking at products that aren't on the market yet under NDA.
Mm-hmm.
And so I wanted to try to, in those senses, it would be something we'd be getting directly from a manufacturer, but we couldn't share it with anybody.
Yeah, so you would get that
one
from
of those things where we'd want to be able to have a separate repository, or some way we could have information from a manufacturer that wasn't shared.
Yeah, in that case, you would get it from the manufacturer. You would take that BSDL into our tool, and that would give
Mm-hmm.
the tool the information it needs to make the comparison.
Okay. Yeah, I was just wondering how all of that was set up and handled.
In this case, let me see if I can administrator. I think I have that typed correctly. There we go. I knew I'd get it. So if we edit the boundary scan project, I'm going to open an existing project, Scan Express demo board. So here we go through definition of the project. We give it some names, some information to help us understand what it is later. We define our tap interface. So in this case, we run at 10 megahertz, 3.3 volts. And then we define our boundary scan chain. So each of these entries is a BSDL file that we obtained from the vendor. So in all of these cases, these are publicly available. Altera, now that they've been acquired by Intel, may not be so publicly available, but we were able to obtain these. If you didn't have a method to get it from the website, then you go to your FAE or to your vendor, whoever your contact is there, you request it. At that point, you can go in, you add a device, you browse to the file, and you load it in.
Okay.
So in our case, we actually have our own repository here of boundary scan BSDL files. We can't share them.
I understand. Completely understand.
So let's cancel out of that. Any other questions?
Yeah, I have one more question. So when you're talking about the match, so you basically compare what is stored on your database, right?
Mm-hmm.
So, for example, if you want to match the ECID, then how are you going to match it?
Well, in the case of ECID, we don't actually match it. We only report it back. We've tried to design the tool in a way that we can update it later if somebody were to, example, have a system where they had like a list of ECIDs to match to, or if they wanted a certain format to be able to send to their vendor and ask if it's authentic or not. But right now, all we can do is report it. I think you can also specify, but I have not tested this, a pattern matching. So you can make sure the ECID matches a specific pattern. I'm not sure how useful that would be for authentication purposes.
Right. Correct. Okay.
Yeah, so all we can do with an ECID, we report it back, and we also verify the length of it. And I would also point out that we only do the simple version of an ECID. The 1149.1 2013 standard, much like the 1687 standard, identifies a more complex process of reading out the ECID using procedure description language, PDL. The tool does not currently do that automatically.
Right. No, because the reason I asked that when you try to detect, say, let's say recycled or remarked ICs, the problem is you need to trust somewhere the person who is performing the test at the supply chain. And often those guys are not trusted. So you exactly don't know that the chip is on the system, it has been used before or not. Because if someone reads the value and don't report it, no way you can verify that, well, this is the IC had been sold like 10 years back. So that part is kind of like a problem. So that's why, so far as I know, like there was some initiative initially, like 5-6 years back, to detect those recycled ICs by using ECID, but I'm not sure that I didn't see nowadays in any such push in that direction. So there are some activity on the physical unclonable functions. I don't know you are aware of that or not. So it basically creates a unique ID based on the device rather than just direct printing the numbers on your device. So that way it prevents an cloner to clone the ID.
Yeah,
so of course you can get your remarked IC, that's for sure. If the ICs are upgraded to a different component, so definitely you can detect that by using your ID matching.
Yes, so if a vendor implemented the physically unclonable function puff, and they could make, for example, the ECID could be a derivative of that, or they could make the puff accessible to us to read out through some probably challenge and response mechanism, right? Then that's something that could be used for authentication. We don't have that in the tool currently.
I see.
But yeah, I'm definitely aware of that, and it seems like the puff seems to be the most popular way of authentication, or at least I don't know if, how much it's being actually implemented, but it's very popular in papers.
Yeah, I think nowadays Xilinx has a big push on their FPGAs, new FPGAs. They have puffs, and so yeah, maybe you can think of that to incorporate on your system.
I lost you for a second there. Do you know how Xilinx, how you would read out the puff information or get that?
So I don't know the details, but what I heard that they have a SRAM puff in their FPGAs, the newer version of the FPGAs.
Okay, I will look into that myself as well. Thank you. Yeah, I know that Xilinx, they have what they call the DNA for every FPGA DNA register that's also Jtag accessible. Okay, any other questions or comments?
By the way, you have a it's done a very good job presenting the Jtag is very good. Yeah.
Okay, thank you. So you have experience, if you've worked with 1687, you're probably very familiar with Jtag itself. It's always difficult to determine the level of detail to go into.
Of course, yeah, agreed.
Okay, well, I want to thank everybody for your time. Looks like we've, if you've got any more questions, I can field them, but otherwise we can go ahead and wrap up. So you can always email me. My email address is bob@corelis.com, and Mike or myself will probably email you that afterward. Actually, you probably already saw my email address when we sent out the invitation.
And please send the presentation to us, like if you can.
Okay, I'll try to get a PDF of that presentation out to you.
Right. Great. Thank you.
Okay, well, thanks everyone for your time, and have a good rest of your day.
Appreciate it. Thanks.
Thanks much. You have a good Memorial Day holiday. Y'all take care. Be safe.
All right.